In this video, we move into IoT healthcare services and applications. IoT-based healthcare systems can be applied to a diverse array of fields, including care of pediatric and elderly patients, the supervision of chronic diseases, and the management of private health and fitness, among others. For a better understanding of this extensive topic, this course probably categorizes discussion into two aspects: services and applications. Applications are further divided into two groups: single and clustered condition applications. A single condition application refers to a specific disease or infirmity, whereas a clustered condition application deals with a number of diseases or conditions together as a whole. Figure 13 illustrates this categorization. Note that this classification structure is framed based on today's available healthcare solutions using the IoT. This list is inherently dynamic in nature and can be easily enhanced by adding additional services with distinct features, and numerous applications covering both single and clustered condition solutions. This section introduces each of the services and applications shown in the figure. So this is the categorization. So we have services and applications. You will learn about their difference very soon. The IoT is Now let's look at the IoT healthcare services first. The IoT is anticipated to enable a variety of healthcare services in which each service provides a set of healthcare solutions. In the context of healthcare, there's no standard definition of IoT services. However, there may be some cases in which a service cannot be effectively differentiated from a particular solution or application. So this course proposes that a service is by some means generic in nature and has the potential to be a building block of a set of solutions or applications. So, for example, if you look at iPhone or mobile phone, so we have the weather service, right? But we also have the map service. But also, we notice that some applications will make use of these different services to reach more advanced functions. For example, if it is a shopping application, it may take into the weather services into consideration so that it can give you a better estimation of the delivery time. Also, it will also look into the map service and provide the most accurate delivery time, just in case there are some traffic accidents or congestion. So that's the relationship between services and applications. So basically, healthcare services are the building blocks that solutions and applications can make use of. So in addition, it should be noted that the general services and protocols required for IoT framework may require slight modification for their proper functioning in healthcare scenarios. This includes need notification services, resource sharing services, internet services, cross-connectivity protocols for heterogeneous devices, and the link protocols for major connectivity. The ease, fast, secure, and low power discovery of devices and services can be added to this list. Now let's look at the different services here. The first one is ambient assisted living, an IoT platform powered by artificial intelligence that can adjust the healthcare of aging and incapacitated individuals is called ambient assisted living. The purpose of AALO is to extend the independent life of elderly individuals in their place of living in a convenient and safe manner. Solutions provided by AALO services can make the elderly individual confident by ensuring great autonomy and giving them human servant-like assistance in case of any problem. So several studies have discovered AALO based on the IoT. So I will leave this reading to you. Another service is the Internet of Health Things, the MIoT, or we can call it. As shown in the literature, mHealth is nothing but mobile computing medical sensors and communications technology for healthcare services. In theory, MIoT familiarizes a novel healthcare connectivity model that connects the 6LoWPAN with evolving 4G networks, now 5G networks, for future internet-based mHealth services. So although MIoT characteristically represents the IoT for healthcare services, it is worth mentioning that there exist some specific features intrinsic to the global mobility of participating entities. This leads to the conceptualization of MIoT services. The use of MIoT services have been examined based on the potential of MIoT for the non-invasive sensing of the glucose level and the MIoT architecture implementation issues and challenges are addressed in literature 24, 29, and 28. The next service is adverse drug reaction, ADR. It is an injury from taking a medication. This may happen after a single dose of a drug or its prolonged administration, or as a consequence of a combination of two or more drugs. Because the ADR is inherently generic, that is, not specific to the medication for a particular disease, there is a need to separately design certain common technical issues and their solutions. An IoT-based ADR is proposed in literature 51. Here, the patient's terminal identifies the drug by means of barcodes or NFC-enabled devices. With the help of a pharmaceutical intelligent information system, this information is then coordinated to sense whether the drug is incompatible with its allergy profile and electronic health record. The IMAP pack has been developed as part of the IMAP box to address the ADR by making use of RFID and controlled delamination material technologies. The next service is community healthcare. Community healthcare monitoring comes with the concept of establishing a network covering an area around the local community. This may be an IoT-based network around a municipal hospital, a residential area, or a rural community. The concatenation of several such networks can be realized as a cooperative network structure. In this regard, a specialized service called communities healthcare is inevitable for meeting collective technical requirements as a package. So we also have some recent development of the community healthcare, which is illustrated in this slide. The next service is children health information, raising awareness around children's health and cultivating the general public, as well as children themselves, on needs of children with emotional, behavioral, mental health problems and their family members are crucial. This has motivated researchers to develop specialized IoT services called Children Health Information, CHI, to address this need in an effective manner. In this regard, an interactive totem placed in a pediatric ward offering CHI service aimed at educating, amusing, and empowering hospitalized children is proposed in the literature. And then IoT-based health services that can encourage children to acquire good nutrition habits with the help of their teachers and patients is also presented in the literature. The next service is wearable device access. Various non-intrusive sensors have been developed for a diverse range of medical applications, particularly for WSN-based healthcare services. Such sensors are prospective enough to deliver the same service through the IoT. On the other hand, wearable devices can come with a set of desirable features appropriate for the IoT architecture. Therefore, the integration of aforementioned sensors into wearable products is apparent. However, the heterogeneity of wearable products and medical sensors uncover numerous challenges for Researchers and developers working towards the set integration. In this context, a dedicated service called Wearable Device Access is required. The integration of wearable devices into applications based on wireless sensing network for IoT scenarios is presented in literature 56. This method introduced a prototype system that can be used in a wide variety of healthcare applications through various mobile computing devices such as smartphones and smartwatches. The next service is semantic medical access. The use of semantics, meanings and interpretation, and ontologies, characterization, and relationships to share large amount of medical information and knowledge has been widely considered. The wide potential of medical semantics and ontologies has received close attention from designers of IoT-based healthcare applications. Placing medical semantics and ontologies on the top of IoT called a separate service called semantic medical access. The next service is indirect emergency healthcare. There are many emergency situations where healthcare issues are heavily involved, including adverse weather conditions, transport accidents, science collapse, and fire, among others. In this context, a dedicated service called Indirect Emergency Healthcare (IEH) can be offered a bundle of solutions such as information availability, auto notification, post-accident action, and record keeping. The next service is Embedded Gateway Configuration, the EGC. It is an architectural service that connects network nodes, the internet, and other medical equipment. From a service perspective, although a gateway may emerge with different characteristics, this requires some common integration features depending on the specific purpose of the deployed gateway. It is in this regard that the notion of the EGC service becomes relevant. The next service is the Embedded Context Prediction. To build context-aware healthcare applications over IoT networks, third-party developers require generative framework with suitable mechanisms, which can be called the Embedded Context Prediction Services. Such a framework is developed in the literature in the context of ubiquitous healthcare. A number of research challenges in context-aware ubiquitous healthcare system has been uncovered in the literature. More or less similar research challenges need to be addressed for context-aware healthcare applications over IoT network, and the context predictor is applied to IoT-enabled remote health monitoring. So those are the healthcare services. Basically, they are the building blocks for more complicated IoT solutions and applications for healthcare.